In this video, we begin chapter 1, which is called differentiation. But before we get into differentiation, we will talk a little bit about limits in this section. Limits in this section will be found using the calculator or using graphs. So you definitely need to have a calculator handy and a calculator that can graph and do tables. Now, what's the idea behind limits? First of all, this is the notation we're going to use. And what does this notation mean? First of all, x arrow a means that the x is going to be chosen very close to a, and a is a number on the x-axis. L is going to be a number that is found on the y-axis. And saying limit of f of x as x approaches a is equal to L means the following. It means that when your x's tend to be very, very close to the number a, the y-coordinates of those x's will be very, very close to the number L, whatever that is. Okay, so finding limits is pretty much equivalent to approximating the height of the curve at a specific spot. Except we don't care what's going on at A itself, we care about what's going on slightly before and slightly after the A. So if I take one of those guys, how big the y-coordinate is going to be. If I take one of those guys, how big the y-coordinate is going to be. That's what we're doing when we're doing limits. So we're not looking at what's going on at the point A. As a matter of fact, there are times when the function does not even exist at the point A. What we care about is what's going on slightly before and slightly after. So for example, if A is equal to 2, we might be interested in finding what's going on as x approaches 2. So in other terms, we might be interested in what's going on with the y-coordinate of 1.999 or maybe 2.00532. Those are all numbers super close to 2. So the question is, if I pick x to be one of those, how big the y is going to be? That's what we're doing when we're doing limits. So like I mentioned earlier, to find limits, we will most likely be using tables or graphing calculators or graphs like this one over here to investigate what the y-coordinates are going to be. And we start with example number 1, and you'll see a lot of the numbers are filled in this chapter because a lot of them involve doing massive amounts of calculations, which can be done with a calculator. That's why I'm going to use the calculator to show you what we're going to be doing. So in the first example, it says f of x is a fraction, x squared minus 9 divided by x minus 3. And the first part of the problem says, what is f of 3? So in other terms, what do you get when you plug 3 into the x's of the f of x? So if you plug in 3 into all of those x's, what happens is you end up with 9 minus 9 over 3 minus 3. And at the end, this will turn out to be 0 over 0. And this is a problem. Why is it a problem? It's a problem because of the 3 minus 3 over here that gives us a 0 on the denominator. We cannot divide by 0. It is impossible to divide by 0. So the answer to this question is no solution. That's why I'm writing no SOL. That stands for no solution. So now we don't know what's going on at 3. So like for example, 3 could be the A of the problem. We don't have an answer where x is equal to 3. There is no y-coordinate to begin with. But that doesn't prevent us from asking what's going on slightly before and slightly after 3. Right? If 3 doesn't itself give an answer, what about 2.9? What about 2.999 and so on and so forth? So that's what we're going to be doing in part 2 of the problem when we investigate what the limit is as x approaches 3. So we're asking basically what's going to happen with the function as x gets closer and closer to 3. And so what I'm going to do is use the calculator to find the answer to this question. So first of all, what we want to do is get into the calculator, into the Y menu where we normally go to graph, and plug in the function f of x, which in this case is x to the power of 2, so x squared minus 9. That's the numerator, so I'm going to close the parentheses there, and then divide by x minus 3. Again, make sure everything happens to be inside parentheses, otherwise you will mess up the problem. So there it is, x squared minus 9 divided by x minus 3. The next thing I want to do is set up the calculator to where I can fill in the table on my paper very, very quickly. And in order to do that, we're going to go second and then click on the button that says window. And you may have different numbers, different whatever showing up on your screen. It does not matter. Eventually, we'll all have the same thing. So ignore the -6. but we want to change the independent variable to be on ask instead of automatic. So in other terms, this will tell the calculator, ask me what the x's are. We're going to leave the second line on automatic so that the calculator will tell me the dependent variable, which is the y, automatically. So I'm going to click down a couple times and then go to the right once, then click enter. This way the calculator now is programmed to ask me for the x value, and in return it will give me the y value automatically. Once this is done, we'll just click second again and then table. That puts us in this menu where we can now punch the numbers in. And the numbers in my case are 2.9. So punch it in, then hit enter. Then 2.99, and so on and so forth. So as you can see, the numbers in blue are 5.9, 5.99, 5.999. If you were to guess a number that they are close to, what would you guess? Hopefully you said 6, because they all pretty much look like a 6. They're like 5.9, 5.99. For all intents and purposes, all these numbers look like a 6. By the way, when I plug in 3 itself, I get an error. That's the reason why in part 1 we didn't have a solution. And then if I plug in 3.001, for example, and then 3.01, 3.1, you'll notice again that the numbers that we're getting are all very close to 6. So numbers before 3, the 2.9, 2.99, 2.999, were all giving us 6. The numbers after 3, all of those, are giving us a number close to 6. So that's the reason why we say that the limit as x approaches 3 is equal to 6. So in other terms, even though 3 itself is not giving us a number, it's actually resulting in a no solution kind of an answer. It's pretty bad. There's no solution at 3. This table that we just made says if you were to pick a number that will go over here, so instead of no solutions, if you want to pick a number, the safest number you can pick is the number 6. What's the reason for that? The reason for that is because all the numbers before it, all the numbers after it, are giving you something close to 6. So the number that you should pick, that one that makes sense, should be the number 6. So in other terms, the limit should be chosen as 6. Now if you notice in this table, I organized the numbers in green to be all slightly less than 3, and I put them first in the table. The numbers in yellow are all slightly more than 3, and I put them after. That's not important. You can change the order, you can do whatever you want. But I did it that way for a reason. Since all of these numbers right here are slightly less than 3, we can say something about this. We can say that the limit as x approaches 3 minus on this function f of x is equal to 6. What does this notation mean? What does it mean to write down x approaches 3 with this exponent of a minus sign? This notation literally means that if you come close to 3, but you're slightly less than 3. So if you look at 2.999, it's slightly less than 3. 2.999 is slightly less than 3, and so on and so forth. All those numbers are slightly less than 3. That's what the 3 minus stands for. It's a symbol that means pick a number slightly smaller than 3. If I pick any of those numbers slightly smaller than 3, I'll notice that the answer that I'm getting is always 5.9, 5.99, and so on, which is always close to 6. On the other hand, if I pick a number after 3, so like one of these yellow ones, so if I pick a number after 3, how do I say a number is after 3? I write down 3 plus. Now, I don't want to pick any random number. I want to pick something very, very close to 3. That's the reason why we write 3 plus, not 4 or 5 or 7 or whatever. So I want my number to be slightly more than 3. That looks like a 3, but slightly more. And I ask what's the limit about when I approach that number. The limit is again is 6, because of those numbers down here are all looking like a 6. So saying that x is approaching 3 plus means that the number you're plugging in the table has to be slightly more than 3. And saying that the limit is 6 means that the result that you got was always something close to 6. So all this is explained in a little bit more of details down here in this little paragraph. So to summarize, saying that limit as x approaches a minus means that the values of x that you're choosing are coming from the left. They are slightly smaller than the number that you have, the number 3, or in this case it was 3. Saying limit as x approaches a plus means that the numbers you're choosing are slightly more than the a. In this case a was 3, so we chose 3.01, 001, and so on. And if the red limit and the blue limit don't match, then you say the limit does not exist. If they both match, then the middle guy is also going to be the same number. So let's say you get 7 here and 5 there, then the middle one will not exist. But in this problem, we didn't have to deal with that situation. All the numbers on the left and on the right were all, roughly speaking, 6. So we say the limit is 6 in the middle. So for this middle limit to exist, the left limit and the right limit have to be matching. The final thing to mention here is that there could be a time where the limit exists, but the function does not. That's exactly what happened in this problem. The function did not exist, but the limit existed.